Welcome to a short presentation on SMPTE 2110 Professional Media over Managed IP Networks standard and how it relates to AES67. My name is Andreas Hildebrand. I'm working for ALC NetworX, the guys who have invented the Ravenna audio over network distribution system. Let's jump right into the topic. 2110 has been published by the Society of Motion Picture and Television Engineers in 2017, and it covers the transport of audio, video, and ancillary data as elementary essence streams over managed IP networks. In contrast to the existing 2022-6 standard, which transports an encapsulated SDI signal over IP networks, 2110 now transports individual essence streams across the network. This standard primarily is targeting at live production applications. So in contrast to 2022-6, which is more focused on the long-haul distribution of readily produced video signals, 2110 will mainly be used in live production environment. The 2110 standard builds on or references existing other standards. For the timing part of 2110, the SMPTE 2059 standard is referenced, which in turn is a profile definition on the well-known PTP, IEEE 1588-2008 standard. For the video transport, the RFC 4175, which is a standard for uncompressed video payload, is referenced. Audio is referenced. For the audio part, the AES67 standard is referenced. And then for the ancillary data transport, a new standard from the IETF, the RFC 8331, is referenced within 2110. The standard compromises several things. And first of all, I want to bring you an illustration how this actually works so that you have a better understanding about the principle. Let's assume we have an SDI signal, usually consists of a video, multiple audio channels, and ancillary data channel. A 2110 sender can now take this signal in and compose individual essence streams out of that signal. So it's de-embedding the SDI signal and is generating individual essence streams. So video, ancillary data, and audio data is living in separate individual streams on the network. Of course, once they are distributed on a network or through a network, on the other side, a 2110 receiver can receive the individual essence streams and can recompose, regenerate the original SDI signal and forward that to any legacy equipment. Well, this certainly wouldn't make a very good example as we wouldn't have the need for the individual essence streams in the first place in this example. The benefit comes in if we just look at the audio parts, typical audio parts of a production system. With traditional SDI distribution, the audio processing devices like an audio mixer would have to receive the whole SDI signal, de-embed the audio to just work with the audio. Now with 2110, the audio processing device just has to receive or register to receive the audio, the relevant audio signals. So it does not have to deal with the large bandwidth of the video signal and do all this de-embedding. It just registers to the relevant audio streams. That can be done because all these streams are usually distributed with multicast on the network. So the audio mixer can receive whatever signals it needs and then distribute the signal and produce whatever output is required. And it's not only getting signals off the network, also for generating signals, like, for example, the cameras. The cameras could provide video and ancillary data streams only, and of course, a number of microphones can be positioned in the studio or around a field, and then these can deliver individual audio signals. And since all of this is fully synchronized based on the PTP standard, on the Precision Time Protocol, all these essence streams can be fully in sync, and so lip sync and any other sync requirements are not a problem anymore. So now if we look at the 2110 suite of documents, we can identify at current 6 documents which comprise the 2110 standard. And we just want to look at the audio parts of 2110 in order to understand how it works and how it relates to AES67. So the documents in 2110 dealing with the linear audio transport, the transport linear audio, are the -10 document, which defines system timing and any definition. So it defines the transport layer and the synchronization. So basically it deals with SMPTE 2059, the media clocks, the RTP packaging, the session description, etc. And then we have the 2110-30 document, which defines the payload format for linear audio for PCM digital audio. And that basically back relates to everything which is being defined in AES67. So basically we can say the audio transport in 2110 is fully in line and compliant to AES67. So whatever is defined in AES67 is what is required in 2110. Well, there are some constraints. The SMPTE wouldn't be the SMPTE if they wouldn't have added some constraints to the existing standard. So let's look at the constraints SMPTE has added to their audio parts with respect to AES67. First of all, we have 2 major constraints we need to be aware of when it comes to synchronization and timing. First of all, since SMPTE 2110 deals with video and is a SMPTE standard, of course, they require that their PTP profile, the 2059 standard, is supported by the devices. Now, luckily enough, since AES67 is also based on PTP, this is not too much of a deviating requirement for AES67 devices. While AES67 requires the PTP default profile to be supported, AES has also defined an AES67 media profile for PTP. And when we look at this AES67 PTP media profile and the SMPTE 2059 profile, we see a very good overlap between these 2 profiles. So in other words, whenever we want to bring AES67 devices into a 2110 environment, the overlap between the 2059 profile and the AES67 PTP media profile can be used to make these devices interoperate nicely and in a synchronized manner. However, we have observed through past interop events that most AES67 support 2059 profile anyway, so natively. Then the SMPTE 2059 added another constraint or requirement to their -10 document. They require that every device which is not intended to become PTP Grandmaster has the option to explicitly set that device to slave-only operation in terms of PTP. The reason for this is because we have seen, or well, SMPTE has seen that in interops, and they fear that situation that devices became Grandmaster which were not intended to become Grandmaster just because the mechanism which determines the best available Grandmaster on a network, which is part of the PTP standard, was not completely implemented in all devices, so that it could happen that some devices believed they were becoming Grandmaster. And what the guys at SMPTE definitely want to avoid is that a microphone somewhere sitting around the field, because there's sort of disturbance, or some devices had a sloppy PTP implementation, then once of a sudden a microphone in the field says, oh, I will become Grandmaster. And in order to simply avoid this, they require that all these devices who are not intended to ever become Grandmaster have an option which can force them to operate in slave only, regardless of any system or network condition. This is not too hard to match. Actually, most of the AES67 devices have this option anyway by design. It's not particularly required by the AES67 standard, but we have seen that most of the AES67 devices have that option anyway. Now, while the former 2 points are not that big of a deal, so to say, we have another requirement which relates to the media clock with respect to the network clock. Now, in order to understand this, we need to have a look on how the network clock and the media clocks relate to each other, how they are generated, and how they, actually how the relationship between the two is. I have an illustration for this. Let's assume, of course, we have a sender and we have a receiver on the network and we have a grandmaster clock. Now, the way it works is that any device on the network, any sender, any receiver, has its own local clock built into that device. And that local clock is synchronized to the grandmaster time by the precision time protocol, by PTP. So in other words, all clocks on the network are exactly synchronized through this IEEE 1588 protocol. Now, once a device has a very precise time, and by the way, the precision of PTP can go down into the dual-digit nanoseconds. So in other words, the deviation between any 2 clocks on a network can be as good as, let's say, 20, 25, 30 nanoseconds, depending, of course, on size on the network and some other variants. So once we have clocks in every device, synchronized clocks, we can generate any desired media clock locally at that device. And since the local clocks are fully synchronized, the resulting media clocks will also be fully synchronized. In other words, if I have the exact same time and I generate the same frequency, let's say a nominal frequency of 48 kilohertz out of that, the resulting frequency will exactly be the same at any participating device. And it's not just the frequency, it's also the phase, which is an absolute synchronization to each other. Now, once I have a media clock, let's say 48 kilohertz media clock for an audio device, of course, I want to generate a stream and send it over to a particular sender. So I generate my stream data, and now the way it works is the transport is established with the RTP protocol. The RTP has its own RTP clock or stream clock. However, that clock is back-related, of course, to the media clock. So in other words, if I have a 48 kilohertz sampling clock or media clock, the RTP stream clock has the same frequency, of course. Most samples are transported, are gathered and packetized in packets and forwarded onto the network. And of course, the RTP stream clock follows the media clock. And once a stream is initiated, there is an offset, R. It's R in this illustration. The offset is established on stream setup. Now, why is there an offset at all? Now, that is because the underlying RFC 3550 calls for a random stream offset for each individual stream which is generated in order to avoid cryptotext attacks. So since the offset, in other words, the RTP clock is part of the stream data, if we use encrypted stream data, and we would know the exact data of the RTP clock, because it doesn't have, once it has no offset to the media clock, to the network clock, then we would know values inside the encrypted part of the stream. And they wanted to avoid this, and so they called for a random offset for each individual stream which has been created and sent over the network. Well, the offset apparently would be constant throughout the stream's lifetime, and since the receiver would have to know this offset in order to relate the incoming data to its local clock, which is the same clock in the network for all devices, this offset for that particular stream would be conveyed from the transmitter to the receiver via the session description protocol in a particular value field. So this value field is the media clock field, which would contain the offset information. So with that offset information, any receiver on the network could relate any incoming stream exactly, precisely to the given network time. Now, and here's the point where SMPTE said, we don't want random offsets. We want every stream to have a zero offset, which actually would relate all streams to the very same point in the network reference time. In other words, from the outside, it would look like all streams would have been created at the initiation point of the reference clock time, which happens to be with PTP, it happens to be the International Atomic Time, which started at the 1st January of 1970. So from the outside, it would look, with this zero offset requirement, as every stream would have been instantiated exactly in the 1st January of 1970. Well, of course, now we have this known value in the RTP streams, but SMPTE says we don't care about these crypto attacks. We have closed environments anyway. These streams never go on to the network, and so they are not object for any deciphering or whatever. Besides, we were not requiring encrypted stream data anyway. So the requirement was to simplify things, get rid of the random offset, and use a zero offset, so that the offset parameter does not have to be conveyed with SDP, and the receiver would not have to wait for the offset information in order to start the stream reception and stream decoding a bit earlier, because it doesn't have to wait for the SDP data to be conveyed. So that is the constraint SMPTE put on the AES67 definition. So in other words, a receiver is not affected at all, because receivers would have to deal with offset information anyway. And if that offset information happens to be zero, no problem. However, an AES67 sender, which would now like to work in a 2110 environment, would have to make sure that the streams he generates and transmits are aligned with the zero offset. Luckily enough, this is not a big deal at all, because most AES67 implementations we have seen so far in the past interrupt use this anyway. So they have either adopted or have been using it from the very beginning. So in other words, this is not really a issue in practice, but of course from the pure standards perspective, or from the definitions side of things, we have to be aware of this particular constraint. All right, and then SMPTE added a few more things to their standards. First of all, they decided, okay, with audio, we want to be AES67 compliant with our audio payloads, audio formats. So the first thing they said, we will define conformance levels for the audio payload format. And level A, which by the way is the only mandatory level, is exactly what has been defined in AES67. So any AES67 sender or receiver can fulfill the mandatory requirements of SMPTE 2110 with respect to audio format. Then SMPTE was a bit worried that 1 millisecond of packet time might be too much, too large for one or the other applications. So they wanted to define lower packet times or shorter packet times, which would provide lower latencies at the end. And so they defined level B, which actually is in terms of sampling frequency and number of channels per packet or per stream, the same as in level A, but now they defined that the mandatory packet time is 125 microseconds, which at 48 kilohertz are 6 samples per packet. Now, if you look at the AES67 standard, it also has optional suggestions for shorter packet times if you want to go with shorter latencies than the 1 millisecond packet time can provide. So, and you'll find this 125 microseconds recommendation also in the AES67 standard. So level B, it's not mandatory, it's an optional conformance level, is again fully in line with the optional suggestions within AES67. And then some people were even more concerned about having the ability to distribute more than 8 channels. While you can set up several streams, of course, containing 8 channels each, they wanted to have more than 8 channels in one stream. This is this thinking like, I want to have all my MADI channels in one stream. So, and actually they came up with level C, which requires 125 microseconds packet time again, but this time 1 to 64 channels per packet or per stream. So in other words, with conformance level C, you can now transport fully loaded MADI signals over the network combined into one single stream. So that's conformance level C. And then, since the SMPTE folks come from the video production side, they were also concerned about 96 kilohertz, which is quite often being used in some of the productions. And so they defined levels A, B, C as optional conformance levels. Basically, in the same way they defined the levels A, B, C, but for 96 kilohertz this time. So we have 6 conformance levels, A, B, C, AX, BX, CX, which deal with 48 and 96 kilohertz, and the number of channels and the packet times. And the message is the only mandatory conformance level is conformance level A, which is fully compliant, fully in line with what is being defined in AES67. So if we finally look at the picture, how AES67 and SMPTE2110 with respect to audio transport relate to each other, we can see this nice little illustration here. In this lower part, we have the SMPTE2110 standard with its level A and level B definition for the payload formats. And in the surrounding rectangle, we find the AES67 standard, divided into the mandatory requirements, which is basically the P time of 1 millisecond, and optional recommendations, in this case the P time for 125 microseconds. And as you can see, we consider SMPTE2110 being a subset of the AES67 standard if these 3 constraints, which have been added to SMPTE2110, are met by the respective AES67 devices. So to be very precise, these 3 timing constraints have to be added to AES67 devices, and then the AES67 devices are fully in line or fully compliant to the 2110 standard. So now folks were worried about what about if I want to transport AES3E or AES-EBU audio signal. So that is the metadata which is part of the AES-EBU signal definitions, which can be transported with the full AES3 audio line. Plus, how can I transport nonlinear audio formats such as Dolby E, which requires more than the 24 pure PCM audio bits? And so SMPTE came up with the -31 document. And the -31 document covers the transport of AES3 audio data. So that can transport any 24-bit PCM signal with the corresponding AES3 subframe metadata, so the so-called PCUV bits. Basically, it can transport any of these audio formats encapsulated in AES3, which also include the non-PCM audio and data formats as defined by SMPTE ST337 and 338, which also includes, for example, Dolby E and other non-PCM audio data formats. So this is the goal of -31, basically to transport every signal, every content which could be transported with AES3 standard across a digital link. And the interesting thing is the -30 document is fully built on Ravenna's AM824 payload definition, which in turn is related back to the IEC 61883-6 standard. So Ravenna was always capable of transporting full AES3 signals in a bit transparent fashion, and SMPTE simply had a look at this document and they transformed it into a SMPTE language standards document, and so the -31 document resembles Ravenna's AM824 definition, which has been in place since the definition of Ravenna since the very beginning, and is also already implemented by quite a lot of Ravenna devices. So basically, all the AES67 definitions are retained, like synchronization and how RTP is used and so on. But as a payload format, we not just use 3 bytes, as we do for PCM24, we add another byte for the AES3 metadata in a way which is outlined here on the slide. So you can see the block start and frame start and PCUV bits are part of a 4-byte payload per frame or per sample. Of course, this payload needs signalization in the session description protocol, and we use the same signalization as with Ravenna in -31 as well. So the RTP map would indicate that the payload format is AM824. And all the other SDP parameters stay in place, just as with AES67 with naked or raw L24. So basically, we have a nice compliance between the -30 and -31 format on how to transport L24 and AM824 or AES3 transparent data. So how's the compatibility between AES67 and -30 and -31 in this case? We have seen -30 is a subset of AES67, as explained in an illustration in an earlier slide. But how does -31 relate to AES67? Well, actually, AES67, as you know, doesn't cover any AES3 bit transparent transport. So it's more a question, how does Ravenna relate to -31 and -30, of course? And since for Ravenna we have AES67 built in and the -30 document was built on the Ravenna AM824 specification, we have a full compatibility of all Ravenna devices related to the -30 and -31 standard requirements. Would every device built according to the -30 and -31 requirements be automatically Ravenna compatible? Well, unfortunately not. That is because the SMPTE just has a very, very minimal bare definition on what needs to be required, and Ravenna adds more requirements, like discovery, system discovery, device discovery, stream discovery, and other things. So while technically a -30 or -31 device can be connected to Ravenna devices or vice versa, a naked -31 device or -30 device is not necessarily fully compatible with a full Ravenna system definition, mostly because the further functions and requirements which are defined in the Ravenna standard. So how actually do 2110 and AES67 relate to Ravenna then? What's the difference? What are the commonalities? Here's a final view on this relationship. While 2110 and AES67 have a very minimum set of requirements they are defining within their respective standard documents, Ravenna has the same categories of definitions, but adds more options for each of these individual categories. For example, Ravenna can deal with more than just 48 samples per packet, or we can deal with more than just 1 to 8 audio channels per stream, or we can deal with multiple different sampling frequencies, and so on. And on top, Ravenna adds redundancy definition and discovery mechanisms to discover devices and available streams on the network. So overall, we can consider that AES67 and ST21 are subsets of Ravenna. Actually, from the Ravenna perspective, AES67 and ST2110 are just so-called operational profiles. So within the larger Ravenna definition, we have created profiles which exactly describe what a Ravenna device needs to fulfill in order to be fully AES67 or ST2110 compliant, of course, preserving the full compatibility with the Ravenna ecosystem with the advanced features like discovery and redundancy. So that comprises my short presentation on 2110, AES67, and how Ravenna relates to it. If there are any further questions, you can contact me at any time at ravenna@alcnetworx.de or visit our Ravenna website on www.ravenna-network.com, where you can find lots of information regarding Ravenna and, of course, AES67, lots of resources about AES67 and ST2110. Thank you for your time. Goodbye.